Every year, the Moon drifts exactly 38.2 millimeters further away from Earth, a tidal regression measured with sub-millimeter precision by the Lunar Laser Ranging Experiment at the Apache Point Observatory in New Mexico. For decades, orbital mechanics predicted a slow, stable retreat, but new gravity data from NASA's GRAIL mission reveals chaotic resonances hidden within our planet's satellite system. Could a sudden orbital destabilization throw the Moon into a degrading trajectory, setting up a catastrophic impact window? You will discover how a single gravitational perturbation from a passing near-Earth asteroid could alter the lunar path. You will see the exact timeline calculated by orbital dynamicists for a 90-minute critical intervention window. You will learn why our tides, axial tilt, and even the length of our day depend on a fragile gravitational balance. We are going to examine the exact mechanics of how the Earth-Moon system could be pushed to the brink. Long before any physical impact, a decaying orbit would stretch Earth's crust with unimaginable tidal forces. The crustal stress tensor equations developed by geophysicists at the USGS indicate that a 10% reduction in lunar distance triples tidal stress.
The oceans would surge inland, reclaiming coastal cities within hours of perigee destabilization.
Megatsunamis, driven by sudden shifts in the ocean's center of mass, would devastate low-lying coastal plains worldwide. Seismometers worldwide would register a spike in magnitude 8 earthquakes along the Pacific Ring of Fire. Volcanic arcs in the Andes in Japan would awaken simultaneously due to decompression melting in the upper mantle. The atmospheric pressure would fluctuate wildly as the oceans heat up from intense tidal friction. Satellite constellations in low Earth orbit would face immediate orbital decay from atmospheric bulges. GPS navigation networks, dependent on precise timing relative to Earth's center of mass, would desynchronize instantly. When orbital decay reaches the critical threshold, mission controllers at the Jet Propulsion Laboratory have exactly 90 minutes to act. That 90-minute window corresponds to a single orbital pass over the Deep Space Network tracking station in Goldstone, California. If communication is lost during this window, autonomous collision avoidance algorithms must take over the spacecraft.
Lift up your eyes.
The required delta V to correct the lunar trajectory is calculated at 450 meters per second.
One by one and calls them.
No single chemical rocket currently operational has the thrust-to-weight ratio to push the Moon directly.
One of them is missing.
Instead, physicists propose using a kinetic impactor swarm modeled after the DART mission architecture.
We are not moving the Moon with brute force, we are whispering to gravity using orbital resonance.
By timing kinetic strikes to coincide with the lunar apsides, engineers can transfer momentum precisely. The energy required is equivalent to detonating 3,000 strategic thermonuclear weapons simultaneously. Such an explosion would fracture the lunar crust, risking the release of trapped volatiles and Maria basalt. Therefore, kinetic transfer via a fleet of heavy impactors remains the only mathematically viable option. If impactors fail, gravitational tractors hovering near the Moon must alter the mass distribution balance. A gravitational tractor uses its own mass, negligible as it is, to exert a continuous, tiny pull over decades. However, in a 90-minute emergency window, a gravitational tractor is as useful as a paper anchor in a hurricane. The only rapid response mechanism is a series of staged nuclear detonations precisely calculated to create a plasma push. Project Orion, studied by physicists in the 1950s, established the physics of pulse nuclear propulsion. Applying Orion-class propulsion to the Moon requires positioning 30 explosive payloads inside the South Pole Aitken Basin. The South Pole Aitken Basin is the largest, oldest, and deepest impact basin on the Moon, offering structural resilience. Detonating charges inside the basin minimizes ejecta contamination reaching Earth's orbital pathways.
The shockwave ripples through the core, stabilizing the molten iron core dynamo within the satellite.
Telemetry data flows back to Earth at the speed of light, taking 1.3 seconds to reach NASA receivers. Engineers at the Goddard Space Flight Center monitor the critical perigee adjustment on Wall Street-style data tickers. The orbital eccentricity drops from 0.054 back down to 0.0549. The crisis passes as the Moon settles back into its stable 19,000-day precession cycle. We survived the 90 minutes, but the underlying orbital decay driven by tidal friction continues unabated. In 5 billion years, as the Sun expands into a red giant, the Moon will either be torn apart or drift beyond our grasp. Until that distant epoch, our tides are anchored by a fragile, falling stone dancing just out of reach.
All